Hello everyone, welcome to the second part of lecture 6. Previously, we talked about binary logistic regression, where the output label can have two possible outcomes, 0 or 1, corresponding to yes or no, or success and failure. This is what is known as a binary outcome and can be modeled using the Bernoulli distribution with a parameter theta. And then we discuss about the properties of the sigmoid or logistic function. And we also mentioned that if we have a linear function of the input, then we can represent that as just a simple inner product or dot product, where x is the input feature. So this is given to us and is known. And w is what we are really trying to find. So that's what shows us how to transform the data in this diagram that we have. And therefore, the model that we have is that the probability that the output y belongs to class 1 or 0 given inputs and parameters is modeled by this Bernoulli distribution. And we can simplify this further and say that the probability that y equals 1 is exactly this probability score that we have here. And we know that this is a probability score because of the fact that the sigmoid or logistic function has this nice property that its output is always between 0 and 1. And if we want to also put the entire expression here, this can be written as 1 over 1 plus exponential of negative a, where a is what we have here, which is this dot product or inner product between w and x. The next natural question is, what kind of loss function should we use here, given the fact that now we are working with these probabilities of each data point belonging to one of the two classes? To get us started, we use the same approach as we did with regression problems, meaning that we are going to use the maximum likelihood approach, given that we have n, here we use uppercase n, samples and observations. And given this, we can start by the principles of maximum likelihood estimation. So remember that in machine learning, we like to solve minimization problems instead of maximization problems. Therefore, we multiply the log likelihood function by a negative sign, and that's what we call as NLL, or negative log likelihood. And remember that the data set has n data points, uppercase n, and we use this subscript n, this little n, to show the index for each observation. Something here to keep in mind, because again, we're in classification problems, is that these YNs are either zeros or ones. So they only take two possible values because of the fact that we are working with discrete labels. So what is the negative log likelihood function? It's the function of the unknowns, and here we use W to represent them. And it's the negative sum of the log of the probabilities, right? The probability that each data point indexed by n belongs to either class 1 or 0, given the input features and the unknowns w. The other thing that also we are doing here, we are dividing this entire time by 1 over n to have more like an average, because also in machine learning, we want to think about loss functions as the average loss on the individual training data points. And as you know, this does not change the solution, because eventually we are going to look at the minimizer of this negative log likelihood function. And if we apply this by a positive constant, it's not going to change the minimizer. The minimum value will be changed, but the minimizer is going to be the same. So that's only a small modification that we have. So let's start from here. So we have negative 1 over n, the summation over n equals 1 to uppercase n of log of these Bernoulli probability mass functions. And I do something here for simplification, and we use it throughout this video. And it's the fact that, when we think about, these types of classification models, we first find a dot product or inner product between the input features and this unknown set of parameters. And this gives us this scalar, which is an. So this is a real valued number, exactly like what we had in regression problems. And now we send this through this sigmoid or logistic function where we get this an, And this gives us this probability measure that I like to call it here mu n. So this goes back to the idea of logistic versus logit function, right? So here mu n is the probability score. So it is what we have after applying the sigmoid or logistic function. And an is a real valued number. It is what we have before applying the sigmoid or logistic function. And this is exactly why this method is called logistic regression, even though it's not really a regression problem, is because technically we are solving a regression problem, except for the fact that we are using this sigmoid or logistic function. That's the key here to make sure that we can translate these real valued numbers, ANs, to probability scores. So with all these here, we have this negative 1 over n, the summation over n of log of probabilities. And we know for the Bernoulli distribution, that was in the first slide, we can write this probability mass function as mu n raised to the power of yn, 1 minus mu n raised to the power of 1 minus yn. And we can do this because yns are either zeros or ones. And now we can use the properties of the logarithm function. So we have a and b. Log of a times b is log of a plus log of b. Similarly, when we apply log of, we find log of mu n raised to the power of yn, we can take this exponent out, and that's going to be yn log of mu n plus 1 minus yn, this exponent log of 1 minus mu n. So this is the expression that we have when we simplify this. So you can see again, using this logarithm function in the log likelihood function is very helpful to make this simpler. And now if we take this negative sign that we have here inside, you can see that we end up with this somewhat complicated term, but you can see that this has actually a very nice interpretation, that we have the average of the loss on the training data points. That's why we added 1 over n. So this is just taking the average, and the loss for each individual data point is what we have here, which is negative yn log of mu n minus 1 minus yn log of 1 minus mu n. And remember, yns are the true labels, zeros or ones, and mu n's are some probability scores. And this loss function is what is known as the cross-entropy loss function. So that's why we use CE, which stands for cross-entropy. It takes two inputs, the true output and the predicted output, which is actually the predicted probability for each class. And this is the loss function. So let's get back to our Jupyter notebook. So this is a summary of what we had. But what we really want to understand is that what this loss function means here or implies. So we can make this even simpler by just writing this as two if statements. So if yn equals 1, then you can see from what we have here, then we get negative log of mu n. And because yn is equal to 1, so this term is going to vanish. It's 0. 0 times log is 0. So therefore, what we get is negative yn log of mu n. And yn is also 1, which means that we get negative log of mu n. And we can use a similar strategy and easily show that if yn equals 0, then this cross-entropy loss function is equal to negative log of 1 minus mu n. So what does this mean? So the nice thing is that we can use NumPy and also Matplotlib to visualize this. So this is exactly a function that does what we have here, that if y equals 1, we have this negative log of mu, and then otherwise negative log of 1 minus mu. The only thing you need to keep in mind that is that this mu should be a probability score. It cannot be just any real valued number. So therefore, in order to find this mu, we're going to use the logistic function that was part of SciPy. And we saw this in the previous video. And using this, we can plot this loss function for these two conditions, y equals 1, y equals 0. So let's start with the case of y equals 1. So what does this mean? So this means that, let's right now look at this purple curve. So on the x-axis, I have the mu n, which is this probability of y equals 1. So this tells us that if the data point that we are working with belongs to class 1, and the probability that it belongs to class 1 according to our classifier is also 1, this is a perfect scenario, right? Because we are 100% confident that that data point belongs to the correct class. So there is zero penalty to pay, and there is no loss incurred here. However, you can see that as we get this probability closer and closer to 0, meaning that I'm moving to the left here, then the price to pay is increasing exponentially. So meaning that if in the extreme case, even though the data point belongs to class 1, and I find that the probability that actually belongs to class 1 is very close to 0, this is a really bad mistake. So we have to pay a huge cost for that. So this goes all the way to infinity. So hopefully we don't get exactly 0, but we don't definitely want to stay away from this area if the data point belongs to class 1. And it's the same exact thing with the case of y equals 0. That's where you can see that there's this symmetry here. And in that case, if the data point belongs to class 0, so we're looking at this yellow greenish curve that we have here. And for this case, it's easier to kind of flip this. So if probability of y equals 1 is 0, then probability of y equals 0 is 1, right? It's always 1 minus this probability for the probability that data point belongs to class 0. So in that case, means that the data point belongs to class 0, and the probability that belongs to class 0 is also 1, because it's 1 minus whatever we have here. And this is perfect. There's no penalty incurred, so that's why we get 0 error. But similarly in this case, if we move to the wrong direction, which is to the right, then there's a huge penalty to pay. So you can see that we have very similar behavior, except the fact that in one case, we want to have this probability of y equals 1 to be as close as possible to 1. In the other case, we want to be as close as possible to 0 because the data point belongs to actually y equals 0. So that's the interpretation of this cross-entropy loss function, which is very important because even in the case of neural networks and deep learning, that's kind of like the most widely used loss function when solving classification problems. So it's important to understand what this loss function implies. So now that we have the loss function, we know that in order to solve the optimization problem that we have to update parameters or weights, we need to find derivatives or gradients, right? And then let's say we can use gradient descent or stochastic gradient descent by finding some solution and then tweaking this solution to find a better solution by moving the opposite direction of the gradient, right? Gradient descent, as the name says. So that's the only piece that I would say we have to cover here, which is very important. And I can go back to my notes because this is something that we need to make sure we understand the logic behind it. So remember, the loss function that we had, the cross-entropy loss function, yn and 1 minus yn, they're both constant or fixed because that's part of the data. The only thing that is really we have to find the gradient or derivative is those probabilities that we had, these mu n's. So the first thing is to find the gradient of log of mu n with respect to w, which are the unknowns or the model parameters. So let's recap what mu n is. So mu n is the sigmoid function of an, and an is the dot product or inner product between this w and xn. When we want to find gradients, as we have done this before, one of the easiest way to do this is to look at the individual elements and then try to generalize this to the case that we have vectors. So let's say W has D elements, right? Because we have here D-dimensional vectors, and for each element of input, we have one unknown element because we are doing this dot product. And let's look at the k location, right? So that's why I'm using this small k here as subscript. So this means that the k location of this wk. And similarly for xn, right? Xn is a vector. Let's look at the kth element, and that's x and k. So whenever needed, we can use two subscripts to make sure that we do the indexing correctly. So this means that now we are ready to find the gradient of mu n with respect to w. And once we do this, we can go back and solve the original problem because the only difference is a log function. And, again, we can use chain rule and take care of that. But let's focus right now on finding the gradient of mu n with respect to w. So remember, this is a vector where each element is the partial derivative or just derivative with respect to the corresponding element. So meaning that we have to first find the partial derivative of mu n with respect to one of these w's, and let's say w index k, right? Because that's what we have done before too. So again, we can use chain rule. So the partial derivative of mu n with respect to wk is the partial derivative of mu n with respect to an, and then an with respect to wk, because we have this sort of like composite function. And the first one is very easy because mu n, if you look at here, is just this sigmoid function of an. And previously in the video that we just had for the first part of this lecture, we found the derivative of the sigmoid function. The derivative of the sigmoid function is the sigmoid function times 1 minus the sigmoid function. And that's exactly what we have for this part. And then for the second part, we have the partial derivative of an with respect to wk. And remember, this is wk times x and k. And so we get the constant, which is this x and k, the kth element of the vector xn. So putting everything together, the partial derivative of mu n with respect to wk is sigmoid of an. And remember, the sigmoid of an is just, again, the probability, which is mu n, 1 minus mu n times x and k. And now we are ready to find the gradient of mu n with respect to w, meaning that the composition of all of these partial derivatives, right? So you have mu n, 1 minus mu n, x and 1, up to x and d, because we have d elements or features. And if you look at it here, you immediately notice this mu n 1 minus mu n is fixed or constant across all these elements. So we can factor that out, and we just end up with all the different elements of xn. So this means that this is just the vector xn. Therefore, the gradient of mu n with respect to w is simply mu n 1 minus mu n xn. And to finish this part, the only thing that we need to do is to take into account this logarithm function. And we know that from calculus, if we have log of x and we find the derivative with respect to x, that's 1 over x. So this means that is 1 over mu n, because that's our x right now from the calculus language. And now also we have to make sure that mu n is a function of w. So we have to also multiply this by the gradient of what we have in front of this logarithm function with respect to w. And here you can see that things get really simple because you have this 1 over mu n and then times mu n 1 minus mu n xn. So these two mu n's cancel and we get 1 minus mu n xn. So we are done with the most difficult part of this gradient calculation, that the gradient of log of mu n is the probability that we find with respect to these unknown parameters, is 1 minus mu n xn. In order to be able to find the gradient of the entire loss function, the cross-entropy loss function, if you recall, we also had 1 minus mu n, and this is also very easy to find using the chain rule, because we can write this as 1 over what we have here times the gradient of this term in front of the logarithm function. And then we have a negative sign here because the gradient of 1 is 0, it's constant, and then we have negative 1 gradient of mu n. So we use a lot this like linear property of gradients here. And in this case, if we calculate this and plug in the value of the gradient of mu n, you can see that the second part now gets canceled and we get negative mu n xn. So we have two parts, right? So we have this gradient of log of mu n, which has this expression, and the gradient of log of 1 minus mu n, which is mu n time minus mu n times xn. And finally, we are ready to find the gradient of the negative log likelihood function. So here, if I remove this gradient, that's exactly the cross-entropy loss function that we had. And again, if you use this linear property, we can use these gradients of these individual terms. And recall that these yns are fixed or constant. That's part of the training data, that we have these outputs, the true outputs. So there's no need to be worried about these terms. We only have to find these gradients of these probabilities. And we just plug in what we found, right? For log of mu n, the gradient is 1 minus mu n xn. And for this second part, we have here negative mu n xn. And if you do the multiplication, we end up with 4 terms. And something that is very interesting here, actually, 2 of these terms, they cancel, right? Because we get yn mu n xn with a negative sign. And then negative times negative is positive, and we get mu n yn xn. And we are only left with 2 terms, and we're gonna do this yn minus mu n xn. We can also take this negative sign inside if we wanna further simplify this. And so we get this very nice simple form in terms of the gradient of the loss function, which is this probability minus the true label, and we multiply this by this vector xn, which is the vector of input features. We can also go one further a step and simplify this by getting rid of this summation, because remember that in some cases you may have millions of data points. So using this summation is not really efficient when you want to implement this using Python or other languages. So the next question is, can we write this in terms of matrix vector multiplication? And the short answer is yes. To see this, let's just consider this 1 over n and define a matrix where these vectors x1, x2 to xn, so these are the n data points, and each data point is a d-dimensional vector. So we're gonna put them next to each other vertically. And this gives us this d by n matrix, because the length of each of these is then d, because we have d elements and we have n columns right now. And then let's say we put all these differences, this mu1 minus y1, mu2 minus y2, and mu n minus yn here. So this gives us n elements, and this is a vector. So you can see immediately we can actually do the multiplication. And this is actually matrix vector multiplication. And we can see that if we simplify this, this can be written as this first element, which is a scalar, times the first vector, the second element times the second vector, and so on, and until we get to the nth column, or the last column that we have here. So therefore, this is exactly, if you compare, is exactly this summation that we have here. So the short answer is, again, yes, we can write this in terms of matrix vector multiplication. And something we have to keep in mind is that throughout this course and in machine learning libraries, including scikit-learn, which is the main library we use for classical machine learning problems, we like to assume that the data matrix is always arranged in terms of rows, meaning that each row of this matrix is a data point, right? So x1 is actually in the first row, x2 is in the second row, and xn. So this matrix has n rows, where n is the number of samples, and d columns, where d is the number of features. And so with this in mind, given that before we put everything in columns, so this means that we have to transpose that data matrix. So when we say x transpose, if x is defined in this way, then x transpose has all these data points in the columns, because we are switch rows and columns, and that's exactly what we get. And then in terms of this second vector that we have here, This can be written as a vector of all probabilities minus the vector of all true outputs. And this part is just vector y, which contains all the outputs, and we did this with linear regression. The only thing is just this vector of all probability scores. And this is easy to find too, because these mu1 to mu(n) are simply exactly what we had in linear regression, just multiplying the entire data matrix by w. So this gives us all the dot products. And the only thing that is we have to add here is also apply this to the sigmoid or logistic function, right? So if you have linear regression, we didn't have any of these sigmoid or logistic function. Now, because we have a classification problem and we're working with probability measures, we have to include these sigmoid or logistic function. So the short answer, again, is yes, we can find the gradient of the cross-entropy loss function, and it has a very nice closed form expression, which is this x transpose sigmoid of x times w. So these are all your probability scores minus the true outputs. And we have also a scaling factor, which again, we are using this to make sure that we can write this in terms of the average. So we have a summary of all these steps here too. So that might be easier to follow. So you can see that we find a gradient of log of mu(n), gradient of log of 1 minus mu(n), and with these two pieces, we can find this gradient easily, and at the end, we get this simplified formula. And in this case, at this point, we can apply a stochastic gradient descent or any variant of gradient descent. And if we use a mini batch of size 1, it's actually very easy, because at each step, at a step t, we have a solution. We just have to subtract this by a learning rate times the gradient calculated at that solution. And you know how to do that if n equals 1, because in that case, you only have to work with that specific data point, which is this probability minus the true output times the corresponding input feature vector. And that way, we can gradually find better and better solutions to solve the classification problem, such that these probability scores match the true outputs or class labels according to the cross-entropy loss function. The final thing we add to this lecture to complete the foundational and theoretical parts of classification using logistic regression, either in binary or multinomial case, is when we have multiple classes, right? So in this case, we can have classes going from 1 to C, and let's say C is greater than 2. So it can be, for example, 1, 2, 3, if it's a 3-class classification problem. So in this case, the main thing that we have to do is replace this Bernoulli distribution that was limited to binary outcomes to the generalization of that to multiple classes. And this is what is known as the categorical distribution, CAT. And in this case, because we have C classes, we need to have C probability scores rather than just having one that we had before. And we know that these probability scores have to satisfy these two properties. First, each one should be from 0 to 1. And the second one property is that the sum of probabilities must equal to 1, right? That's one thing that we always have to make sure. And based on this, we can say that we can have a classification model for a multi-class classification problem where we have a categorical distribution. And then in order to find these thetas, these probability scores, we can have some function of x and theta unknowns, right? Theta is here. Also, you can think of this as, w, but this is just a container for all the unknowns. And in order to actually specifically know what form this theta has, we can write this as the softmax function of w times x. So how does this work? So this is something that we can do this in 2 steps. So here, this w, the weights or unknowns that we have, is a matrix of size c by d, where c is the number of classes, d is the number of features. So we're going to first multiply this w by x. We can do this multiplication because x also has d elements. And if we do the multiplication, then we end up with a vector that has c elements. which is great because we're looking for C probability scores. The only other thing that we have to be careful here is that we need to make sure that we satisfy these two properties, and that's where we use the softmax function. So what is the softmax function? Is this function where it takes C variables like A1 to AC, and we are going to find the exponential of each of those elements divided by the sum of the exponentials of all those elements. So you can see that this denominator is for normalization purposes, so that if we have this C going from 1 to uppercase C, and we add all of this together for different class labels, we end up having with the sum of our probabilities to be exactly equal to 1. And also exponential function, if you think about how this function is, regardless of what AC is, whether it's positive or negative, e to the AC is definitely above the x-axis. And this means that this is going to be a non-negative number, which is what we are looking for. So in a homework assignment, I'll let you prove this, that all these transformations, when applied to these elements of A, the from 0 to 1 and the sum of all of them is actually 1, but it is something that you can see relatively quickly just by looking at the form of this softmax function. So just to recap, if you have the binary case, we find the dot product and then apply the sigmoid or logistic function. But if you have multiple classes, now you need to have a matrix where the number of rows is the number of classes. And on top of that, you have to apply softmax, which is very much similar to the sigmoid function, except the fact that now you can have vectors of more than one dimension. And very similarly, these A values, ACs that we have before applying this softmax function are called logits, right? So logits in general means that you have raw score or unnormalized outputs. And then once you send this through softmax function, you get your probability scores. And then the extension of the cross-entropy loss function for the cases that we have multiple classes, it's very much the same thing. So it has this negative sign. It has the true labels, and then the log of the probabilities. There's only one small thing here that we have to talk about. And the fact that since here we have C classes, one thing that we can do is that we can, for each data point, we can create a vector that has C elements, and only one of these elements is equal to 1, corresponding to the category or group that data point belongs to, and the rest of them, they're all zeros. So this is what is known as the one-hot encoding, right? So this means that if you have, let's say, a 3-class classification problem, and data point belongs to the first class, then you get 1, 0, 0. Or if that data point belongs to the second class, then you get 0, 1, 0, right? So that's why they call it one-hot encoding, because there's only one element that is hot, which is 1, and the rest of them are zeros. So that's how this y tilde is. So this y tilde is a C-dimensional vector, which is this one-hot encoding. And this says that, look at this, the element at location C, and times that by the log of that probability that data point belongs to class C. And the important thing is that since each data point only belongs to one class, so once you really want to find this loss function, you don't need to find this summation over all labels or outcomes. You only need to know which class that data point belongs to, and only compute the negative log of probability that your input belongs to that class. And this is exactly what happened with the cross entropy too, right? Because if you remember, if it belongs to class 1, right, it was negative log of the probability that belongs to class 1. And if it belonged to class 0, then it was the negative log of the probability that it belonged to class 0. And that's exactly the same thing. So this means that if you have like 10 classes, then you have negative log of the probability that that data point belongs to that whatever class it is. So that's why it's important to know that this multi-class classification part is very much similar to the binary, The only difference is that you should be able to find C probability scores when you have C classes. And after that, you just, for your loss function, find the negative log of the probability that data point belongs to that class.